Namaskar and welcome to this 20th lecture titled Mass Concrete in this series of lectures covering hydration, porosity and strength of cementitious materials. This is our second lecture closely related to the previous one, where we dealt with heat of hydration of cement and related issues. Now here is the overview of what we will talk about. Various engineering applications such as dam construction requires a large amount of concrete to be used. Since cement hydration is an exothermic reaction, the heat generated may lead to thermal stresses. In this lecture, we will discuss the mechanism of these thermal stresses and how they are generated, factors that affect the temperature rise, prediction of stresses and temperature, and methods to tackle the detrimental effects in these cases. The discussion that we will have today will be briefly a review of the heat of hydration from the last class, introduction to the subject of mass concrete, its definition and so on, the whole idea of temperature rise in concrete, thermal stresses and strains in concrete, evaluation of thermal stresses, and how do we address the problem arising out of thermal stresses in mass concrete. Now coming to a review of what we have already done, we know that cement hydration is an exothermic process leading to rise in temperature at the core of a very large pore, and in those cases the outer surface cools faster than the core of the section. You will recall that in our discussion yesterday, in lecture 19, we talked about two issues, the heat evolution and the heat dissipation. So if the dissipation is not good enough for whatever reason, there will be temperature rises, especially in the core. The surface of concrete tries to remain in equilibrium with the environmental temperature. By thermal expansion or contraction, the temperature differential between the core and the surface induces thermal stresses which are tensile in nature, and that is what we will study today. And since concrete is essentially a material which is weak in tension, this introduces cracks in concrete which are referred to as thermal cracks. Now coming to the definition of mass concrete, the ACI or the American Concrete Institute has defined it as any volume of concrete which is large enough to require measures to be taken to cope with the generation of heat from the hydration of cement and the attendant volume changes to minimize cracking. This definition obviously makes it clear that it is not only the volume of the pore, but also other factors which will make it important or imperative for an engineer to consider a particular pore of concrete as mass concrete or not. Now let us understand these issues a little better. Let us consider these two shapes or the two geometries in which the concrete is cast. One is a large block and the other is a slab, maybe of the same volume. Now the block has a lower area to volume ratio than the slab. The slab has a much larger area. Now if the same amount of heat is liberated in the two cases, it is easier to remove that heat from the large surface of the slab than in the block. Given the geometry, the thermal gradients in the block will be more severe than in the slab. So essentially what is being said is that if the volume of the two pores is the same, the amount of heat generated in the two cases will be the same. However, when it comes to dissipation, the dissipation is largely related to the surface area, and since the surface area of the slab is more than that of the block, the dissipation is easier in the slab. Further, the distance here is much smaller than the distance here, and therefore the chances of a thermal gradient developing through the length of this slab are much smaller than the thermal gradients developing over this half length. So these are the kind of considerations which become important when we talk about temperature rises. Now, put slightly differently, if we compare mass concrete with structural concrete or normal structural concrete, the characteristic feature of mass concrete that differentiates its behavior from that of structural concrete or normal structural concrete is its thermal behavior. In most structural concrete, most of the heat generated by the hydration of cement is rapidly dissipated and only slight temperature rise is expected or arises, and therefore in most of our normal construction we do not really need to bother about thermal stresses and the heat of hydration of cement. Now, to take an illustrative example, let us consider a 2 meter by 2 meter by 2 meter concrete block which is cast against the ground. This volume of concrete is 8 cubic meters and the total surface area is 24 square meters. Now, what we have as details is there will be a 2 meter by 2 meter area which will be in contact with the ground, and 4 faces 2 meters by 2 meters each in contact with the formwork and then the atmosphere. Basically what we will be doing is we will be casting a block like this, and the bottom here will be in contact with the ground, and these 4 faces will be having formwork and the atmosphere outside, and one 2 meter by 2 meter face here on the top is the one that will be exposed to the atmosphere. Now, as against this, if we consider a situation where a 200 mm thick concrete slab measuring 6.3 meters and 6.3 meters is against 6.3 meters and 6.3 meters is cast against the ground, the situation will be the volume of the pore will be the same, 8 cubic meters, and the total area will be 84.4 meters against 24 meters that we saw last time. In this case, 6.6 into 6.6 will be in contact with the ground, 4 small faces of 0.2 into 6.3 will be in contact with the formwork and then with the atmosphere, and a 6.3 into 6.3 will be exposed to the atmosphere at the top. If we now look at a situation like this as a model, we say that concrete is cast on a glass plate. So this is a glass plate, and why it is a glass plate is something which will become clear very soon. And if this is the original length of the concrete which is cast, on account of rise in temperature of this block or the slab, there will be a rise in temperature and that will lead to an expansion. So this is the length after expansion. We must remember that this will happen when the concrete is still relatively young and is more deformable. Now, this expanded length of concrete is obviously higher than the original length. So the original length was only this much, and we have seen so much expansion that has happened on account of rise in temperature. The importance of having glass as a model is that it does not provide any friction, and early age concrete is easily deformed, as I said earlier. So now this not providing any friction is something which we must understand or keep note of, because the illustrative examples that we talked about, there the concrete was being cast against the ground, and ground does not have the same kind of friction characteristics. So the ground concrete interface does not have the same kind of friction characteristics as are being modeled now. Here what we are saying is that because it does not provide any friction, the concrete block is free to expand like this, and the expansion here at the interface is the same as the expansion on the top. Now, the concrete does not remain at a elevated temperature all the time. Once it cools, the concrete wants to come back to its original position, but this contraction is resisted and the concrete finally reaches an intermediate position. So, now this resistance comes on account of two things. One is that concrete at that early age is rapidly hardening, and therefore, it becomes more difficult for concrete to contract, as it were to contract, compared to the situation when it was expanding under the effect of elevated temperature. The second part of the resistance comes from the restraint which the interface offers. So, once we understand the principle that yes, there is an original length, there was an expanded length, and finally this is the length after contraction, we will be able to understand the concept of thermal stresses or thermal strains much better. So, effectively what has happened is that we have the original length here and we have the final length here as shown, and the concrete is under a virtual tensile strain. So, if this is the original length where the concrete wants to come back to, and this is the length where the concrete is being held, this leads to a virtual tensile strain which can be looked upon as caused by a virtual tensile stress, and this is related to the modulus of elasticity of concrete. Now, in other words, if we know the strain, how do we convert this to stress? What we must understand, or what we try to model, is that this strain is arising out of a stress. There is some kind of a stress acting on the concrete which has caused this kind of strain. In other words, this strain is effectively equivalent to this kind of a stress, and when we are converting these two, we need the modulus of elasticity of concrete. Now, this modulus of elasticity of concrete is obviously not that of hardened concrete. This has to be that of the concrete at the age at which we are talking about. And if this tensile strength is exceeded by the tensile stress, the concrete will crack. We must remember that when we are talking of this is stress and this is strength, both are actually functions of time, and therefore we must keep in mind a discussion as to how the tensile stresses develop over time and how the tensile strength develops over time. Equations and guidelines for 28-day strength of concrete, the 28-day modulus of elasticity of concrete are not really helpful. To recapitulate this discussion, let us look at this picture. We had an original length like this. Because of the temperature rise, it expanded to this place with no restraint. That is what the glass plate was doing for us. If now at the time of cooling or during cooling or thereafter, if it is fully restrained, that is the degree of restraint is 1, then the concrete will be held right here, and all this will become the restrained strain in the concrete. Now, most of the time the degree of restraint is not 1, and if the restraint is anywhere between 0 and 1, there will be some amount of change in the length of the concrete, but there will be a certain amount of strain which is still remaining, and this strain is what we need to take into account when we are talking about converting the strain to the thermal stress. Recapitulating, now if the surface temperature is allowed to deviate greatly from that of the core, thermal cracking will develop. Basically what is being said is that if on account of heat of hydration, the temperature of the core of concrete is allowed to be greatly different from that at the surface. So, let us say Ts and the core, if there is a large difference between these two, then there will be a certain amount of thermal gradient that will develop, and that is what will induce the cracking. As we have seen, if the thermal stresses are greater than the tensile strength of concrete, we will have cracks. When it comes to the dissipation of heat, as far as evolution is concerned, the parameters are pretty clear. It largely depends on the cement type, the composition, and so on. When it comes to dissipation of the heat, parameters such as the conductivity of concrete or the specific heat of concrete, the coefficient of thermal expansion of concrete and the aggregates, diffusivity, all these parameters become important, and these have to be taken as parameters for the concrete at the early age. This is something which we had talked about yesterday also in lecture 19, that essentially we are looking at a situation where from the temperature at which the concrete is placed, on account of the heat of hydration, the evolution of the heat and the dissipation, the balance of the two, the concrete reaches a certain peak temperature, and that peak is reached at a certain time. And of course, at the end of the whole process, the concrete goes back to the ambient temperature. And this is a graph which I had shown the other day also to give you a quantitative feel of the numbers involved. The peak temperatures are in the range of 60 to 70 degrees, and that would depend obviously on the size of the pore, that is the size of the block and so on, and also the time. In this case it is about 24 hours. So, we must understand this picture here has two very important components: the time at which this peak temperature is reached and the peak temperature itself, because that tells us how much is the delta T which will be involved as far as cooling is concerned. As far as the factors that affect the temperature rise are concerned, apart from the cement content, there is the cement composition. If we have a cement with low C3S and low C3A, we can expect lesser of problems, less temperature rise. Most mass concrete structures do not need early age strength, and therefore slower hydration is usually not harmful to the construction. We have cement fineness as another player. Lower fineness with slower hydration is preferred, and then there is the geometry of the pore, as we have talked about in this discussion earlier, where the large volume to surface area ratio are more susceptible to thermal cracking. There are other factors such as the coarse aggregate content, the coefficient of thermal expansion of the coarse aggregate, use of supplementary cementitious materials. Obviously, it is known that the hydration of cement is a exothermic reaction. Now, if we reduce the amount of cement and replace it with some other material which takes part not in the primary hydration but the secondary hydration, we have seen earlier that when water is added to the cement, we get hydration products and calcium hydroxide. The supplementary cementitious materials, they primarily react with the calcium hydroxide to give more or less similar hydration products, and that is the whole beauty of it. That is, this reaction is not exothermic, and therefore if we want to control the heat that is generated in a certain pore, if we replace a part of the cement by supplementary cementitious materials, we would go a long way in controlling the amount of heat that is generated. And this graph here and similar graphs which are available in literature will tell us how using supplementary cementitious material helps us reduce the temperature rise over time in different concretes. Another important parameter that affects the temperature rise is the placement temperature. Lower ambient temperature produces less temperature rise, lower volume to surface ratio produces less temperature rise, and these are the kind of things which engineers keep playing with when they plan a mass concrete construction. Now let us try to understand how can we evaluate the danger or the vulnerability of a concrete to thermal stresses and cracking on account of thermal stresses. One such measure is the thermal cracking index, which has been defined as the ratio of the tensile strength and the maximum tensile stress in concrete. Obviously, since it is the ratio of the strength to the stress, a higher value of TCI is better from the point of view of susceptibility to cracking. The tensile strength for the purpose of calculating the TCI can also be taken to be at the time when the peak thermal stress occurs. So, the TCI, we must remember, is time dependent and hence needs to be calculated at different ages, and the minimum should be taken for further study or investigation. This aspect we had talked about a little earlier when we said that the tensile strength and the tensile stress are both functions of time, and therefore, if we are comparing the two, we must make sure that we carry out that comparison over the entire period of time that is of interest to us and find the minimum value, because that is what should govern our design considerations. This here is from the guidelines of the Japan Concrete Institute, the JCI, and we can see that as the thermal cracking index increases, the probability of thermal cracking reduces, and therefore, it is up to us to define or to pre-decide a specification on what is the TCI that we are willing to work with. In other words, what is the probability of cracking that we are willing to live with in a particular construction. So, in general, limit the value of thermal cracking probability is given as 5%. In cases where the structure is required to be totally crack free, a limit may be lower than 5%, and when a high risk for thermal cracking can be tolerated, a value higher than 5% may be allowed. So, these are the kind of guidelines which an engineer must lay down when he is deciding on the kind of concrete to be used. Yet another player in this game comes in the form of steel reinforcement. Obviously, if we put steel reinforcement, the whole discussion in terms of the expansion of concrete or the contraction of concrete and so on, it changes. So, there are two ways of looking at it, or there are two aspects to this problem. One is that in reinforced concrete the steel is already there, and therefore, that steel provides additional restraint. In the other situation, we may have plain concrete, but we provide reinforcement in it to account for the thermal stresses. So, in either case, it is the effect of the presence of steel bars in the concrete which needs to be taken into account, and also we get involved with the parameter called crack width. It is much easier to say that yes, concrete will crack, but what will be the width of that crack? That is also an important parameter, and we are not getting into the details of computation of those values, but as engineers we must know that yes, these are important parameters, and if we want to or if we need to, we should go to an appropriate literature and find out the kind of guidelines which are available. So, for example, it is given here that one may fix the maximum allowable crack width to be 0.05 millimeters, the thermal cracking index to be 1.85, the probability of cracking to be 5%, and then try to see how much steel should be provided or how much additional steel should be provided in order to ensure that these parameters are met. Where does this discussion have applications? It has applications in massive foundations, bridge piers, thick slabs, concreting in nuclear plants, structural columns, and so many other places. And this is another graph which we talked about yesterday, which showed how the thickness of the concrete member affects the temperature rise, and we can see that if the thickness is varied from 300 mm to 1000 mm, there could be a substantial difference in the temperature rise that we see. This is another text. Here we are writing the same thing in a more illustrative form as text, where we say that a 0.15 meter, that is 150 millimeter thick concrete wall, can become thermally stable in 1.5 hours, whereas a 1.5 meter thick wall would require a week, and a 15 meter thick wall would require 2 years, and a 152 meter thick wall would take 200 years to achieve the same degree of thermal stability. Now, of course, we do not sometimes cast a 152 meter thick wall all at once, or for that matter even perhaps a 15 meter thick wall all at once, and that gives us the flexibility or the idea that, well, can we cast this in parts, and that is where the importance of a construction plan comes in when we are trying to address the problems of mass concrete. This is just another illustrative example of how modern tools are available to help us carry out the analysis in terms of determining the probability of cracking or the crack width. We take a wall. This is a wall with the footing, and we try to model it using finite element methods and so many other tools which are available, and try to understand areas which are more vulnerable to thermal cracking, less vulnerable to thermal cracking, when the thermal cracking is likely to happen, and so on and so forth. Now, coming to the steps that can be taken to address issues in mass concrete, we have alluded to them earlier in our discussion. We could use low cement content and or use supplementary cementitious materials, use low fineness of cement, higher aggregate content, change the aggregate mineralogy, change the type of cement in terms of having low C3A and C3S, high 4AF, high C4AF and C2S, which is a relative issue. Then there are things like adequate curing. We can also get into measures such as pre-cooling the ingredients or using cold water or ice in concrete. Now, these help us lower the placing temperature of concrete. Then there are methods which are available which are called post-cooling, where we do that with cold water network of pipes, alternative methods of placing and compaction, use of fly ash and slag is supplementary cementitious materials, and construction planning, where we talk in terms of how much should be the lift height, what should be the pour volume, what should be the placing schedule, because we know that if we want to cast a large block of concrete, we can break it up into smaller blocks of different sizes. So, if we are able to carry out a simulation which says that, well, if we cast smaller blocks, we will have lesser problems as far as thermal stresses are concerned, but at the same time that will become more difficult to do. So, it is a simulation of that exercise which helps us arrive at an optimal solution as to what is the best thing to do. Now, this is a list of text and reference material which will help you better understand the topics which have been covered, and I would like to thank you for your attention.